The radio wave communications are being used since a long time, and whenever the communication uh, needs to be established at a high frequency, right? Uh, we are going to use slightly different type of transmitters and receivers. Okay, and that falls under the specific name. It is called as the uh, HF radio. Okay, so it uses specific certain parts which are basically hardware based as well as the software based, right? We have hardware as well as the software controlled uh, architectures for this purpose. Okay, now let us look at the block diagram of such system. Okay, right. First, we are going to see the transmitter, and then we'll look at the receiver block diagrams. Okay, okay. Basically, this designing of the high frequency radio is actually an extension of our normal radio wave transmission technique. Uh, we will be beginning with what is called as the okay. Let's start with the message that we want to send. Could be something like right. So this is we can actually start from the microphone itself. Okay, the first part. The microphone. And we know that this is in the analog, right, mode, or this is working with the analog signals. So signal capture happens in the analog format. Then we need a digital ADC, right, analog to digital converter, to convert this input signal into the digital. Then we have this is analog to digital converter. Now, once you have a analog to digital converter in place, now the signals come into the digital format, right? Then we have the next part that is actually we process the signals in the digital domain. So DSP comes into picture. Here, before you transmit any signal, you perform what is called as an interpolation. Okay, so the next block is about interpolation filter. All right, so this filter provides something like you may have during the ADC, you might have lost some of the samples. Okay, so those samples will be uh, the missing samples will be recreated by the interpolation filter. Okay, that's what is the work done by this. Then There is what is called as a mixer. Normal mixer is simple multiplications of two signals. So one is a incoming signal with a cause or sign. But since right now we are in the digital domain, we use the similar concept, but on the in the digital domain. So we call such mixer as a digital mixer. This is digital mixer, right? Digital mixer actually takes the input, the one of the input that comes the is from the interpolation filter, and the second input is always coming from it should be an oscillation, right? But we use the digital oscillators over here. Okay, so the digital oscillator generates oscillations, right? As per the requirement, like the required frequency, required amplitude, right? So at the output of this digital mixer, we are going to get the oscillations or the digital samples at intermediate frequencies, something like IF, right? Compare this with the what you call as the analog receivers or transmitters. You have the intermediate frequencies coming into picture at the somewhere in the middle, right? During the design of the communication components, we have intermediate frequencies coming into picture, right? So let me write that over here. So at this point, I'm going to get what is called as the digital samples, digital samples at IF. So that is intermediate frequencies, right? Now, actually, there is a name for uh, the bundle of these three components. Okay, this actually is a specific part of our HF radio, and this is called as the digital up converter. Right. So whenever you want to go to a very high frequency, our requirement is that I have to perform the modulation and put the particular what you call samples to a very high frequency signal like a carrier, right? So when our intention is to perform that, right, we have to use the up converters over here. Okay. Right. Once this is done, now we can use any of the digital modulation techniques, right? So, so the next component is this is digital modulator. Use any of the modulation techniques, right? We want so that the high frequency signal is obtained at the output. Okay. Now, once you use this modulation, now this is still in the digital domain. I want this to come back to the analog so that you transmit, right? So before the transmission, our expectation is that signal comes back into the time domain because the hardware which actually maps the signals and transmits on through the antenna, right? That expects analog, not in the digital mode, right? So we have to use the next component as a that is again bringing this back into the analog. nature. So yes, so this is digital to analog converter, DC. All right. Once you bring it back, now uh, the output of this DAC is analog signal at high frequency, right? Higher RF frequency, right? So then let's move further. Now we have to use it. Okay, this could be something like I bring into the RF frequency. I have to use the RF converters, right? Some of the RF converters that we need to use to fine tune the frequencies to the exact right exact band at which you want to send. All right. So that is uh, yeah. We used RF converters over here. Right. Then we need to put the appropriate amount of power, right? So that your signal travels the required distance, right? So for that reason, we use the power amplifiers at the end, okay? And then once we have the power amplifiers output, that can be given to the antenna. So that will transmit your signal. So here you have the RF signal. So I get the high frequency RF, right? Signal, which you can actually send, right? So basically, this part is even sorry. Just a second. Okay. So here, the up converter is actually it can be even implemented using the software, right? As I earlier told, uh, we have the software as well as the hardware processing that can happen for HF radio, right? Whenever you use a software components over here uh, for this purpose, right? It's also called as a software defined radio. Okay, so in what's the change? I will tell you there. You may not have these two components, microphone plus this, because your message is expected to be present in a computer in that case. Okay, so you have the message ready with you, right? It can be the audio format, the recorded format already. Then you use some sort of software which performs the digital up conversion using the DSP architectures, right? Any of the DSP algorithms can be applied to do this as well. Okay, so in that case, you see this circuit is not required. You will use a software to do this job. Okay, that's the first thing. Otherwise, another option is right. You implement this part on an FPGA board, right? So it's again software, right? So there is a hardware. FPGA is going to do the job, but anyway, you will write a code to right, right. So you can write a code over there, and that will perform this job. Okay, and the output whatever you have, then you give it to the required circuits, right? Take it away from the FPGA board and give it to the circuits will convert the rest of the jobs. Okay, so overall the high frequency radio transmitter looks somewhat like this. Okay, there are various modifications depending upon what is the output frequency you want to send, right? So Again, if you want to go to very high frequency, you need some more filters, right? And the design becomes complicated over there, right? But the general representation of a software defined radio plus the high frequency, right? Software means, as I told, there is a software part coming into picture. Otherwise, you implement everything using a hardware, right? Means that is a HF radio. Okay, and another version is there where you can use the analog modulation, right, later on convert into digital. That's also there, right? So instead of directly converting analog to digital first and then using a digital modulator, right, you can definitely use the uh, digital convert analog modulate it first to analog, then you convert into digital. That is, yes, sure, sure. Okay. Okay, this one you want? Okay. And the other modification is that if you want to have a faster communication using the what you call as the this HF radio techniques, you can even shift to uh, any of the other advanced modulation techniques such as OFDM. Okay, that is possible. In which again the block diagram slightly changes in that modulator part, right? So you have to perform the appropriate uh, steps. You have to bring the appropriate steps into picture that is required to generate, say, OFDM, right? If you recall the what is called as OFDM, it's a orthogonal frequency division multiplexing, right? So wherein you try to send multiple symbols or multiple in case of digital it is symbols, right, over multiple orthogonal frequencies, right, wherein you automatically avoid the inter-symbol interference, plus you are going to do what is called as right, you can send the data faster, right? Parallel channels do exist over there, so because of which you can send it faster. But anyway, it has its own disadvantages, such as you need to have the something like complex hardware, because there is a FFT coming into picture internally, right? So you need to have the hardware that supports faster calculation of FFT. So then what you call as the interference, right, can be avoided. Also, you can actually bring the cyclic prefix in place so that the delay associated with the whole channel can also be avoided, etc. Many things are there, right? So that becomes more complicated, right, but more efficient, right? We have multiple options like that, right? Those are the changes that we can try to bring when it comes to the uh, modification according to our need to get a better what you call better communication. Okay, so this is a high frequency this thing. Now let us come back and see what happens in a receiver. Okay, this is a transmitter. Let's go to the receiver. Right, so here we are expected to do the reverse of what has been done in the transmitter. Okay, so uh, let's try to do that. So first, let's say we receive the signal from the antenna. Okay. Now this received signal from the antenna. First, it is uh, given to a filter that actually selects only the bands of frequency required, right? So this is uh, frequency selection filter. Then, once the appropriate RF frequency has been chosen by this from the received components, you retain only those frequencies. It's like a band pass filter. Okay. Then it will go to a tuning circuit, that is RF tuner. So this gets tuned. Right. As soon as this is tuned, again, I know that I'm coming back. I have to come back to the digital domain in order to, right, do the processing, right? So I have to go for a, this is analog. I want digital. So we use ADC, right? So at this particular point, we have digital samples. We are going to obtain the IF, right? Once again, intermediate frequency. So basically, we this part is here. I'm going to get the analog IF, intermediate frequency. Okay. At the output of the ADC, I'm I'm going to get the digital samples. All right. So digital samples at the intermediate frequency I get. Right. So now my intention is that I have to do the down conversion. I had the up converted frequencies values over here, right? So I need to do the down conversion, right? Again, this is going to happen in the digital domain, right? So let's bring this into the down converters. First, I'm going to use the mixer once again. That is a digital mixer. And mixer needs another input that should come from the digital oscillator. Generates the samples of oscillations of a particular frequency. Plus, this is passed because uh, when you multiply two signals, right, using a mixer, you have two types of frequencies coming up. Like normally you multiply cos into cos, right? You get a cos squared function, which is 1 plus cos 2 theta. You see that there is a high frequency 2 theta coming up. Normally we don't want that, so we have to eliminate that component, right? The high frequency component needs to be eliminated by using a low pass filter. Again, this will be a digital low pass. Okay, so we are in the digital domain, so this has to be a digital filter, right? You can design using FIR, IAR, whatever, right? Doesn't matter. Now, uh, 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 yes, yes, yes. Please take your time, no problem. Yeah, yeah, sure, sure, sure. No issues. There is a LPF, right? To select the appropriate frequencies out of uh, after the mixer generates an output, right? This is normally because you have two sorts of frequencies coming at the output of the mixer. because of the mixing operation. And this part, the three components all together, we call it as the digital down converter. Yes, the previous block diagram was a transmitter, and this is a receiver block diagram. Okay, digital down converter, which converts your uh, high frequency component, that is digital IF, into the digital low frequencies. Right. Once you have the frequencies, the frequency data with you, you can go for the demodulation. Right. This is still the modulated wave. I have not performed the demodulation yet. All right. So this is perform the demodulation using a demodulator. So according to uh, what modulation was taken in the transmitter side, you have to do the reverse over here, right? Like if you had chosen PSK, you'll do the PSK demodulation over here, right? And so on, right? So this provides you the output. Now the output will be uh, called as the digital baseband signal, right? So baseband because it is in the normal frequency which was used before the modulation, right? So same frequencies are obtained over here, and it's a low frequency, and you are getting the signal back, right? So this is not IF, right? The digital baseband signal, right? That is obtained now. Now you can go back to the analog if you want, and you can give it to the speaker, right? For the in a normal way of radio, you can do this. So let's write the this is digital to analog converter and provide this to the speakers for audio output. So that completes the diagram of this. Now, let's see what are the modifications, right, in this. So the modifications that can be done here is if you want to go for a software controlled part, that's a software defined radio receiver, right? The down converter can actually be directly implemented in the computer. Okay, so in the computer you will run a software, right, based on the which actually executes some sort of DSP algorithms, right? Right. Correct, correct. So you can give the output of ADC, directly bring it into the computer, read a particular port in the computer where the input is available, right? Bring it the sampled values, which are the digital intermediate frequency samples, into the software part, right? Software will read those values, and those values will be processed, okay, according to the algorithm that you are using. So the down conversion can be done. Okay, so normally there is another method uh, that is you can see here the instead of this the down converter, right? There is another process called as a decimator. The one decimation which actually, right, converts your very high frequencies into some sort of lower frequencies, right? But that is not the baseband which we require. Something like earlier, if you remember, I told that some missing samples will be added up, correct, in this process, up conversion. So that means you are adding something means you are converting it to a high frequency, okay? But here I should do the reverse, right? It is in the high frequency, I have to convert this into low, right? So you do some sort of reverse process that is called as a decimation, right? So there you do the interpolation. Here you are supposed to do the reverse of that process called as decimation. Okay, so that's another term, right? If you refer some of the books, you may find these terms over there, but ultimately they are uh, going to do the similar job, whether they call it as up and down converter or the interpolation and decimation, right? You are going to get the similar outputs at the end of those blocks. You may see such blocks as well when you refer other uh, other books or something. Okay, fine. So ultimately, you can replace this on the software side a specific code, right? So the advantage in the software side is that without changing the hardware, right, you can try to use varieties of modulation techniques. You can use varieties of DSP algorithms as well uh, to make modifications in the output, in the radio wave output, right? That is possible if you use the software part. So that's why the SDR type of radio transmission became more popular. Okay, right. You can control on the software side itself. You don't, because if I want to change from AM to FM on a hardware side, you have to change the complete circuit, right? But you see that is not required, right, in case of a software control, right? So as discussed already, you can even replace this part. You can implement this part on a FPGA, right? And you can get to much higher frequencies, because the operating frequencies of FPGA is much higher compared to the other normal hardwares, right? So by writing the code, right, to control the FPGA, you can even go for much higher, what you call it, frequencies, right? So FPGA or the software part. So in the software part, what else happened is, so uh, all the components that is after this digital down converter will be inside the computer. So you don't have to go for a demodulator circuit. That will also be implemented in the form of a software, right? You get a signal, right? Just convert that into the analog and simply play it over the speakers of the computer, or you can even use a software to convert that signal into a wave file and you save it, right? See, these are the advantages on the software side, right? So again, if you are using that kind of circuit, so first half will be the hardware part, followed by you have the software coming into picture. So normally the softwares are used to replace the digital part, because digital parts normally process the digital signal. Same digital signals can be processed even on the software side, because software works on the digital signals, correct? Right. So it's one and same ultimately, right? So the software part, if you are using, say, sorry, in the transmitter side, if you are using the higher order modulation like OFDM, then the circuits will be more complicated, because all the conversions you did in the during the modulation should be converted back, right? Should be reversed, right? So for example, in order to avoid the multiple copies of the same signal being received at the receiver, you add something called as a cyclic prefix. Okay, so that you need to remove here. So you have to have a different circuit for doing that job, right? Then there will be multiple channels over which you receive the signal. This is to avoid the ISI, intersymbol interference. If that is the case, the multiple channels should be combined into a single channel before you go to the next process, right, over here. So that is also an extra burden for the, in terms of the circuit's complexity. It actually increases the circuit complexity. So you are going to reduce, you have to uh, add that component at any cost, right? Again, you may have the FFT circuit over there. You need a IFFT circuit over, right? So circuits, overall complexity of the whole circuit depends upon, first thing is what is the communication technology you are using, right? What modulation you are using, right? Can be analog, digital, right? Again, so according to that, the complexity is going to change. right? And the second parameter that decides the complexity here is are you using software based or hardware based, right? So if you use software, right, the most of the digital parts, right, you don't have to build any circuit for that, simply use the software, right? Appropriate software and coding is required to do this, right? So the major components are up converters and down converters when it comes to the digital part, right? Analog parts will be definitely you have some tuners circuits, right? You can tune it to the appropriate frequency to receive those parts. Normally we cannot build using the digital components. Okay, so only this frequency selection filter, like a band pass filter, needs to be designed. Antenna should be analog part. Analog, it's antenna, the selector and the tuner will be the analog components that must over here. Then after that, you convert into digital and process everything in the digital part. At the end, you may require a DAC to get back the audio clip, right? Right. Otherwise, you can simply save it in using the software side itself. You can save it into the computer's memory, right? Maybe in the wave format or any of the specified audio format. Okay, so this whole thing is called as the receiver part of what you call as the high frequency radio. Okay, so now let's look at some more details about this. So the first part is what is the requirement basically? What is the requirement of such a right system when you have the normal radio? Correct. Normally, the radio will alter the transmission and receiving parameters, right, to avoid the interference. Normally, normal radio means it's that you have one transmitter, multiple receivers, right? And right, the radio, that device will try to alter the parameters of transmission and reception, like modulation, frequency, power, etc. Right. But in this high frequency, right, uh, you can potentially tune to any frequency band and you try to receive any modulation across a variety of frequency, right, using hardware or the hardware plus software. So here the advantage is one device serves multiple purpose, right? Normally, right, you are going to use it in the military applications, right? And the uh, transmission and the communication between the vehicles, right? This is the basic usage. Now something like you can have these uh, transmitters and receivers designed to serve the, say, something like a single purpose. For example, maybe a cell phone, a wireless router, the GPS receivers, AM FM radio, all of them, right, you can use. All right, then uh, you can actually change the modulation technique in order to bring the security into picture, right? So what you can do, if you use the software part here, the advantage is that all of a sudden the transmitter and receiver can switch their modulation technique itself, right? Because let's assume that somebody is hacking to the system and trying to receive, trying to intercept the right transmission, right? So what you can do here, right, randomly you can switch from ASK to say QAM, right? So nobody knows what you are using right now. So somebody might have tuned to your say previous communication technique, maybe it's PSK, right? So at a particular time you will shift this randomly from right, PSK to QAM or PSK to something else. Maybe simply you use ASK file. Okay, right? You see that what happens now, the uh, whoever is trying to, right, listen to you doesn't know that what's the current situation, right? What's the current technique. So that means change the modulation technique, right, on the go, as and when you want, you can change, right? Also the circuits can be modified or you can use the very powerful algorithms inside the software in such a way that you can avoid the noise, right, in the reception side. Okay, so because of the software, you have more advantages over here, and you can write the advantages. You can note the advantages of whatever I mentioned so far. And the one more advantage is that you can write the code and implement various DSP algorithms. Right, you can do a lot of trial and error, right, method. So which one is the best suitable uh, algorithm for your application? You can do trial and error, because writing a code and running something is much easier than building up a circuit and testing, correct, right? And also, since you are using the what you call programming over there, you can bring the modular coding techniques, right? You can write different modules, integrate them, right, on the software side, and then do a lot of testing over there, right? So again, the another advantage is that you have varieties of data representation possible when you do a software based control, when you bring the software controls. For example, maybe, right, you are in the digital domain, but you want to send something which are in the bit sorry on which look like bits only, right? Like I want to communicate in the bit level, right? Yes, possible, right? You have bits with you, right? Some data was there, right? We brought into the digital domain, and it's in the form of bits now. Definitely you can convert, you can send bits as it is. Just make the appropriate conversion of the digital signal to the analog and send it, right? That's fine. Now I say no, I don't want to go with the bit level. I want to convert that into some code so that I enhance the security by applying some coding techniques, right? You do the coding, and coding results in symbols, not the bits, correct? So like I had a 1 0, I convert that into a letter A, right? Like 1 1 is B for me, right? Like that. I converted that into some symbols, and you want to go ahead with the symbol level, right? You want to go ahead with the symbols, means yes, that is also possible. You see, this is not possible when you do it in the hardware side, correct? So even if you try to do something on the hardware side, only one technique you can implement, because the hardware is completely different when you deal with the bit stream, when you and it's completely different when you go with the code stream. One of them you can implement, but you cannot change, you cannot swap. That is not possible, but that becomes possible whenever you have the uh, software part coming into picture in this. And you also have the advantage, as I that I already mentioned, modulators can be changed as and when you want, right? So you can I write four different blocks of codes, one for the PSK, one for ASK, one for FSK, one for QAM, etc. Yeah, right. So randomly you can switch, right? Simply switch the code blocks so that you change the whole modulation techniques, right? So again, on the software side, I will tell you another advantage, right? uh, on the receiver side, you can perform what is called as the channel estimation, right? Channel estimation is very important in the communication, because normally the channels have a time varying frequency response, right? Time varying in the sense, say maybe during sunlight, the nature of the channel is different, and as the time changes, right, sunlight reduces or increases, so you see that channel's property is going to change with respect to time, right? There is a change at in the for example, morning, you it actually passes some frequencies. Afternoon, those frequencies are blocked, some other frequencies will be allowed, correct? So that kind of response, right, you need to make an estimation, right? Right. If you make an estimation, reception could be uh, the reception's characteristics can be improved. So again, hardware part, yes, you can do something like only one time, right? Multiple techniques do exist for a estimation. For example, I want to bring a machine learning technique in picture. But if you do a hardware side, only one time. I cannot bring any other time. But software means yes, right? You can sorry, you can actually do the changes. Correct. Right. So physical implementation has those restrictions which can be overcome. You can overcome that using the software part, right? Another very important aspect, again, I have not drawn over here in the receiver side. There is one concept called as the gain control, AGC, automatic gain control, right? We have two options. You can do that on the hardware side or the software side. Hardware side means you have need a hardware component somewhere here, right, at the beginning, right? Yes. So you use, I preferably before the frequency selection filter, you use a gain control. But on a software side, again, you can implement inside the software component itself, right? So normally we have some, if you go for higher types of or very complicated type of modulation techniques, uh, you may find in the block diagram, there are two more components for timing adjustment and the carrier recovery, right? Two components might come, right? If you refer any other books, right? So you may find two things there because it's normally it is non-coherent, right? So you don't know what frequency you are sending. So you need a carrier recovery tool that actually performs the identifies what is the carrier frequency basically. Okay, so that part may be extra. Then the timing, because digital is all about timing, the sampling time should be synchronized, right? So for that you need a timing device, okay, to recover the original clock frequency used in the transmitter, right? So those are the two components which are extra, okay, that may be present if you refer any other books or any other resources, right? Don't get confused, that's one and same. Ultimately those two jobs will be done by those devices, okay. All right. So variety of circuits are also available, right? But this circuit what we have discussed now is a general one, okay, which helps us in understanding the whole process, okay, whole process of the HF radio, right? We need to design each and every component for to meet our specifications, right? Once that is done, that means your design is complete.